All right? And first things first, let's remember, the complex number came from the idea of these numbers over here, the square root of negative 4, should have some answer to that. Okay? And the idea was that, let's call that the square root of 4 times the square root of negative 1, because this wasn't really legal to do before, by what we were using. Weird things will happen, but the square root of negative 1 we'll define as I, and we'll call it the square root of 4, or 2I. Now, okay, so somebody was just thinking, why, if I square something and I get negative 4, shouldn't I get an answer? And the answer is they came up with these imaginary numbers, and they said that doesn't make sense, but we'll use those. Now, some of you probably think that in math, we just keep trying to confuse you and teach you different things, and just when you think you got it, now we come up with something different. In this case, it really was somebody saying, I think this should work, and where can we go from here? And so the math people developed these complex numbers on their own with this idea of, well, now what makes sense is that the square root of negative 1 equals I, and let's go from there. Let's see what things will work. We end up treating I pretty much just like a variable and kind of forgetting what it is, and just every once in a while, when certain things happen to it, we go back and remember, oh yeah, I was the square root of negative 1, or what we're finding out today, I squared is negative 1, things like that. So they develop all this math, and it seems really great, and the rest of the people are saying, you guys are wacky, your math people, you're out there, imaginary numbers, yeah, right, that's what we need, okay? And along comes somebody who says, well, you know what, I'm having a problem here with some science, with what I'm doing, and I need to kind of model what's going on. And guess what? Imaginary numbers worked, all right? And I bet you're using it right now today. Do you guys know what that is? In the room I'm in, there's electricity. And that electricity is powering some lights and some other things, and it helps charge that. And electricity, the flow of electrons, can be modeled by complex numbers, by real and imaginary numbers. And so electricians, when they're planning out a building, actually end up using complex numbers. And that's one of the uses. There's some other things, and your book gets into a lot of these fractals and other things. But there's other things where it's used, but that's the most common where I can say, look, that's why we teach it, because there is a use for it out there. There's somebody that uses it. In fact, it kind of is in the modern world. So if it hadn't been that way, I bet you complex numbers would have just fallen off to the side, and real number, imaginaries would have been, oh yeah, that was something, that was kind of cool, but we'll leave it out there. But we actually have a use. So now that we have a use and we have a reason why to keep studying these, let's go about and graph these, okay? And so they say, well, what's the most common way, what should we do with these complex numbers? Well, they have two parts, remember. I hope you can see way over here. They have a real and an imaginary part. Maybe you can't, so we'll go down here, 2 minus 3i. There's a real and there's an imaginary part. Okay, there's two parts to it. And that's what a complex number is. And so all of our old real numbers, they still fit complex because they just had a complex part that was 0. Okay? For instance, 5. Well, 5 is 5 plus 0i. So that's a real number, but it's also complex, if you want to think of it that way. And the negative 2i, that's another one of them. If we just say we have negative 2i, well then you got to remember that the real part was 0. And all of these are complex numbers. To graph them, all we do is we just put the real numbers on the x-axis and put the imaginary numbers on the y-axis. Whoa, okay? I had students that were getting that wrong on like placement tests and like ACTs. They asked them to pick out the graph and they couldn't do it. Well, it took me a second to figure out, oh, we're getting this wrong? Are you, okay? And we showed it to them and everybody was fine after that. So be aware, this could be a standardized test question on like an ACT or SAT, just to catch, and it should be fairly easy. So we take a look at this 2 minus 3i. All that means is I go over here 2, I go down 3, there's my point. We'll call that point A. Okay? We'll go 5 plus 0i. We'll call this point B. And then go 5 plus 0i. So we're going to go 5, whoop, 4, I need another one here. And 0i, there we go, call that point B. And then we'll call this one point C, and we go 0 and negative 2i, over 0, down 2i, put a dot, there's C. And you can see all three of those. Okay? Well, the next thing I'm going to show you is what happens if, so now I've graphed complex numbers. Whoop. Now, what about an absolute value of these? Okay, so what's the absolute value of A, and how does that compare to the absolute value of B? Well, we're math geeks. We like to have a number or one thing that tells us about it, and tells us some information. And so they talk about what is the absolute value of a complex number, and they say, well, what should it be? Well, look at the graph, and what it should be is which one is bigger, right? Because isn't that what distance is? You know, absolute value is distance, and the further the distance, the bigger the thing is. And so, but really absolute value in the real numbers is how far is it from 0. So if it's way over here at 5, but that one's over there at -10, which one's further from 0? -10, right? And so we want to see that same idea. Which one of these is further from 0? But now it's a plane that has 2 dimensions. And so they're saying which one is further from 0. You know what that means? Which one has the longest radius? Okay? Now, that one's easy. That's 5 away. This one's easy. It's 2 away. This one, how can you figure out how far away that is? You got it. It's called Pythagorean's theorem. So for some people, a squared and b squared, and then you got the c squared there. So all we have to do is we know that a squared plus b squared equals c squared. And so all we have to do for the absolute value of this is go ahead and say, hey, what's 2 squared plus -3 squared, and then take its square root. That's going to be 4 plus 9, its square root, that's square root of 13. So that's basically the absolute value of a. How big is a? How far away from 0, 0 is a? How far away is b? Well, I really don't have to do this, but I can. 5 squared plus 0 squared, its square root is the square root of 25, which is 5. And then down here, it's 0 squared plus -2 squared, its square root, so that's 0 plus 4, its square root, which is 2. Now notice, what part did I harvest when I do a and b? So, by definition, if we have a complex number, then we call that complex number a plus bi. We've got to put it in that form. Then its absolute value of a plus bi is a squared plus b squared, its square root. Notice, is there an I in that at all? No. There's no i's. The I is gone. So we're stripping the complex part of it, the imaginary part away, and saying, hey, I just got the numbers that are out in front. So don't get that wrong. Whenever you square something, it's positive. Whenever I square the next thing, it's positive, and I add 2 positives to get that value that I'm going to take the square root of. Okay? And so that is distances. Now the next thing we'll do is, now that we're comfortable, hopefully, with graphing them and finding their absolute values, figuring out how big they are, then let's go ahead and add them and subtract them. Okay? So what I'm going to do is I'm going to give you 2 numbers here, and I guess it doesn't really matter what my 2 numbers are. 2 plus 3i, -4 minus 5i. I don't like that. Sorry. We'll make that -2 plus 3i and 4 minus 5i. Sorry. Okay. And so what we're going to do is we're going to say, let's take a plus b. Well, good. It's -2 plus 3i plus 4 minus 5i. Now I may not feel, okay, that's going to make this tough, right? No. That's real. That's real. Add the 2 real parts. -2 plus 4. Okay, what's that going to be? 2. Add the 2 imaginary parts. 3i plus -5i. That negative sign's got to go with it, right? There is no such thing as subtraction, only adding an opposite. Okay? And so, 3i minus 5. Okay, oh, they have something in common. What do they have in common? 3 plus -5. They both have an I in common. Sorry, changing colors on you. This is 2 plus -2i. So we added those 2 numbers and got 2 plus -2i. You just add the like terms. Add the real parts, add the imaginary parts, we're done. So what if I told you to take a minus b? And I'm just going to get a different color here and stick with it. A minus b. Well then a is the -2 plus 3i. Minus b, which is 4 minus 5i. Okay? We have to keep this parenthesis over here, we have to keep that separate. So I know this is really -2 plus 3i plus -4, and subtracting a negative is adding a 5i. Now I've gotten rid of all of the subtraction, and it's all addition with opposites, and, subtracting a negative is adding a positive. And I go, negative 2 plus negative 4, negative 6. 3i plus 5i is 8. There, that's the subtraction. Notice, we didn't get the same thing. We don't get the same thing. Addition and subtraction are not the same thing for real numbers, right? 2 plus 5, 7. 2 minus 5, negative 3. We don't get the same thing there. We don't get the same thing here either. So, that is addition and subtraction. Okay, now I'll come back to this in just a minute, but let's make sure we've built a pattern. I think I taught this next part earlier, and I guess I was jumping ahead, because now they talk about what happens if I multiply I by itself. So I is known as the square root of negative 1, but that's really just I, okay? I to the first. I squared. Well, that's the square root of negative 1 times the square root of negative 1. And by definition, we say that that is itself, which is negative 1. I mean, because a square root of something times, isn't that what a square root is? The thing that when multiplied by itself gives you negative 1. So that's negative 1. And remember, I cubed, we said was that times that times that. Well, that's like having I squared times I. Well, we just told you that I squared was negative 1. So negative 1 times I is the same as the opposite of I. And then I to the fourth is like I squared times I squared with my, and that's negative 1 times negative 1, which equals positive 1. Okay. Well then, we said, okay, what happens if I ask you for I to the fifth? Well, now that it's more than 4, why don't I just rewrite that as I to the fourth times I? I to the fourth was 1. This is 1 times I, otherwise known as I. I to the sixth is I to the fourth times I squared. I to the fourth we know is 1. I squared we know is negative 1. I to the seventh. I to the fourth times I to the third. 1 times the opposite of I is the opposite of I. And then I to the eighth. Sorry about, we're just looking at you. I to the fourth times I to the fourth. 1 times 1 equals 1. I hope you see the pattern that you can predict I to the ninth right away. Hey, wait a second. I to the ninth. Boom. We're going to go up here. It's going to be this. It's going to be I. I to the 10th. It's going to be negative 1. I to the 11th. It's going to be the opposite of I. And I to the 12th. It's going to be 1 again. And so it's not so much, notice here, 12, 8, 4. They go together. They're all equal to 1. 11, 7, and 3. They all go together. They equal the opposite of I. 2, 6, 8, no, 2, 4, no, we missed the 4, right? 2, 6, 10. They equal 1. And the last one up here is 1, 5, and 9. They all equal I. So when somebody says that they have I to the 23rd, you just got to figure out which category does it fit in. Does it fit in the category here, 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 or here? There's 4 categories. And those categories are based upon the division. If you think about it like this, 23 divided by 4 is 5 and 3/4. Remember, 3 is what we call the remainder. Okay, so what I'm doing is I'm dividing this exponent by 4, but you know what? I don't really care that it goes in 5 times. I care that the remainder is 3. Because what does that mean? It acts here like I cubed. Which means this will be equal to the opposite of I. Okay? So any power that I have, I'm going to go out on a limb so you guys can see this. I to the 251st, that's 251 divided by 4. Goes in there 6 times, 24, 11. That goes in there 2 times, 8, 3. Guess what? It equals I cubed, the opposite of I. Okay? So we should be able to figure out any of those powers and reduce them. And the last thing for today then is let's put that to use, because I've showed you that a couple times now. Let's put it to use, and let's go ahead and multiply. So the last thing for today is let's take A and multiply it by B. A times B. This time I think the color will be appropriate.